I'm Stuart Halloway, and we're going to talk about Clojure's time model. This is the concurrency and parallelism track, and I'm not going to spend a lot of time talking about concurrency and parallelism, at least not at first. So we're going to talk about modeling the world, and we're going to talk about the model that we use today most of the time, which I'm going to give a name. I'm going to call the total control model. And argue that it causes a lot of difficulty, not because it sucks for concurrency and parallelism, although it does suck mightily for concurrency and parallelism, but because it's actually just not a very good way to model the world anyway. And then I'm going to talk about an approach that can be better. Not the only approach, not the only better. There are entertainingly, there are lots of ways to do it better than we're doing it right now. So this is not the only model. It is the model that's implemented in Clojure, although a lot of the ideas here may be useful in other settings as well. So to begin with, we're going to define time. And it's going to stay kind of physical like that for a while. So what is time? Time is when things happen. Time has to do with ordering of events. I went down to lunch. I came up and gave this talk later. It has to do with whether things happen at the same time, right? We're all able to do this together because we are all here concurrently. Right? We are all in this room concurrently, so you can listen, I can talk, whatever. You can throw things at me. Right? We're all here together. And for our purposes here, time is relative. So I'm not going to talk today about syncing vector clocks and things like that. I'm not worried about absolute time. We're trying to simulate absolute time. And a lot of things that we do as programmers, we don't care about absolute time, we care about relative time, right? We care that $100 got deposited to the bank account before $50 got removed from the bank account, and so forth. Second term we're going to define is identity. And identity is continuity over time. And identity is built by mind, right? It's built by your mind. So as you watch me walking across the room, actually, am I going to ruin this if I walk in front of the, a little bit? It's going to go all fuzzy. As I walk across the room, how many people in here think there was a Stuart Halloway over there a couple of seconds ago, and now there's this person over here who's totally different? Right? So there's a name for the condition that you have, right? If you have trouble assembling identity over time, this is great. Those who have seen my last couple of talks, I've been spending a lot of time in the Oxford English Dictionary researching talks, which is not normally where I end up, but looking at these words. And it turns out that if you have trouble building continuity over time, if you can't perceive identity, that's called schizophrenia. Right? But this is something that sane minds do, right? We build a notion of identity. I walk over here, I'm still me. None of you are struggling with, oh, I see some blue and some khaki color over here. Holy crap, is that the same thing that was still over there? Right? We perceive identity and we don't have a lot of trouble doing that. And identity is sameness across perception. Right? And so this is something that's happening, right? You see me, you hear me, you see other things in the room, and you're assembling identities in your mind. And identities themselves are not names. Right? So when you look at me, you might say, oh, that's Stuart Halloway, but that's not really the identity. Right? Because you might say, I don't know his name. That's the speaker at the front of the room. Or you might say, that's some random person. Right? So there are a lot of different names that might be assigned to identity, but the name is not intrinsic to the notion of identity. And importantly, when we take this to programming, identity can be composite. Right? I am composed of multiple parts. And in most software systems, if we were going to model me as an identity, we would model me as an identity. We would not model my left arm as a separate identity, unless we were building an organ bank or something like that. But so there are some modeling questions. But in general, we pick identities, and we know in the real world that identities can be very small and granular, but they can be big and composite as well. The third word we're going to introduce is perception. Perception means to become aware via the senses. And importantly, and this is going to really resound throughout the talk today, perception is uncoordinated. Right? In other words, I don't have to participate in you perceiving me. Right? And in fact, I can't go, you're not perceiving me anymore. right? It doesn't work. Right? I don't get to choose whether you're going to perceive me. If you're in the room here with me and you choose to look at me and we have light and so on and so forth, right? If the environmental conditions are correct, you get to perceive me and I don't get to do anything about it. And this perception provides values, which are snapshots. I mean, they're literally snapshots. Everybody close your eyes for a second. Come on. Don't fall asleep, though. I know it's right after lunch. You can open them again. While your eyes are closed, you still have a mental picture of what's going on, right? You could still be thinking about me if you were looking at me right before you closed your eyes, or whatever you were looking at. You have that snapshot in your head. And who controls how quickly that snapshot decays? The perceiver or the object perceived? The perceiver gets to decide how quickly that perception decays, right? If you have a really crummy memory, or if you have a bad visual memory, right, your perception of me may have decayed immediately, right? You closed your eyes and you couldn't tell me what color shirt I was wearing. My visual memory is pretty close to that bad. Right. But it depends. On the other hand, if you close your eyes and then I spontaneously combusted, you could continue to ponder your perception of me for how long? Forever. For as long as your mind chose to hold on to it, you could ponder that perception of me for as long as you like. These things that we perceive are values. Right? The unit of perception is a value. And a value, if you're thinking about it in terms of time, is a point in time of an identity. So here I am, this is a value. Now I'm over here, that's another value. If you wanted to, you could still be thinking about this value. Right? If I did some kind of crazy gesture, right, you could keep thinking about that gesture and keep thinking about that value, even though my value has moved on. Do I have to stop moving so that you can think about some old position that I was in? No. If we filled this room with 1,000 people, would I slow down because of contention in perception? No. Right? It's a really great property. And this property is not unique to me. Right? No matter how many people we put in this room until we start to hit other kinds of limits, right? No matter how many people we put in this room, I'm not going to speed up or slow down. It's like, oh, crap, you're looking at me. I can't move as fast. Right? We don't have that problem. The next term is action. Action is change to identity over time. And action is independent of what's going on with people who are doing perception. Right? So, again, this is the point, right? I don't slow down because you're looking at me. Right? I can proceed with whatever action I'm undertaking. You can look at me, and those are independent things. However, my action will make a new value available for you to perceive if you care. You might not care. You might close your eyes. You might stop looking. You might look at something else. But if you want to, then you can. And finally, when you get down to thinking about this in software, actions might have many possible semantics that we want to care about. Right? So you might start talking about things being synchronous or asynchronous, or coordinated or uncoordinated. So there are a lot of different semantics, and you probably would not want, when writing software, to be stuck with one. Right? Oh, we have to always do things synchronously and coordinatedly. Well, that's kind of high overhead, depending on how it's implemented in software. Maybe we want to do async and uncoordinated in other circumstances. Now, I think that everything that I've said so far is reasonable. I won't use the weasel word intuitive. I'll use the weasel word reasonable. Right? It really doesn't matter. But it's straightforward enough to follow, even if you're being introduced to it for the first time. Then we have this other model, which is how we write software. And this model is really inherited from the 1970s, if not earlier. And the model says that I sit down at a computer which I am the absolute master of. I have complete control of it. And that computer has one processor. And that computer has one notion of memory, right? There's no notion of memory hierarchy. Right? There's just a memory that we can interact with. And we write programs this way. And of course, there's only one thread in our programs. And I would argue that everything beyond that, which is, how long has it been the case since that was true? Was it ever true? Right? But our actual hardware model has diverged from this model continuously from any point you want to pick. And if this was ever true, it's certainly far from true now. Right? We have multiple processors and multiple threads, and we don't have total control of everything on our systems. Right? We're doing multitasking, and we're competing with other processes for resources. But our way of modeling this is still, we start with this kind of presumption of global total control, single processor, single memory, and everything else is, holy shit, how do we recover from the fact that that's not true? And that's the way we work in mutable, object-oriented programming. And what this ends up meaning is that everything I said before about time and identity and values and perceptions is left to the programmer. Right? And it's left to the object-oriented programmer to define how those things should work. And in general, we do not define how those things work system-wide or language-wide. What is our unit of granularity for defining the time model in our programs? Right? Probably the class. Maybe even the instance. Right? This is really crummy reuse conceptually. Right? We keep building a time model again and again for everything. And the time model we usually have is we don't think about it. Right? We don't think about change over time. We just build programs and then say, oh my God, there's another thread. We're in big trouble. And so when you go down this road and try to roll your own, you have a lot of problems. The first problem is that time basically doesn't work. If you're going to build programs out of mutable objects, then what happens to past? Right? I'm here, and then I mutate. Right? You set the value that a pointer points to something else. What happens to that old value? It's gone. It's completely gone. There is no memory. Right? So modeling mutable state, or modeling the world with mutable state, says that there's no such thing as memory. Right? But even the present is unreliable. Right? Because in general, values in our systems are not, or the things we would try to use in place of values, are not immutable things. What are they? Variables. They're variables, and they're variables that point to things that can change, which means you have things like, you can see me in a state that I never actually was in, right? Because I was partially through being updated, and some part of me is updated and some other part of me isn't. You can see things that aren't even real. So the present's unreliable, the past doesn't exist. Identity, well, you're in big trouble when you try to model identity this way, because if you're going to model identity at all, you're saying that I'm going to have change over time, and I better have locking to protect that change. But locking does not model identity in the sense that you can't walk up to a synchronized block in Java and say, oh, I know what the identity is. Right? What is the mapping? And originally Java, right, tried to pretend like this was true because, in the Java 1.0 and 1.1 days, when people first started doing threaded programming, we just said we're going to synchronize the entire object. But when in a Java program is an object actually an identity? Rarely. Right? If you modeled me, I might have a sub-object that represented body parts. I might have sub-objects that represented capabilities. All of those might be aggregated together in my identity. And so what we're left with for a model for identity is convention. Right? We have to use convention to say, oh, in this system, in this part of the world, then this lock means that this identity can be safely updated. Perception is totally ad hoc. If you want to think about me, what do you have to do? If you want to think about this value at this point in time, what do you have to do? Copy. Right? There's nothing else you can do because you have no idea what that is. And is there a copying values, surely that's an easy service that would be provided to you by your programming language. Right? So surely you could just point at a value and say copy it, but no, you can't. And in fact, I would argue that the situation with perception is so bad that you might as well say it's impossible. Right? Because making things copyable requires per class, per instance work by the programmer, and even then it's not thread safe until you have a convention for assigning identity back to that. Ditto for values. And don't get me started about action. Right? Side effects are, and the last piece here is really where the functional programming folks come from. Right? There's side effects all over the place. Right? There's no one place in our system where we say action happens. Where does action happen? Anywhere. Does mutation in our system actually represent action in the real world? Often not. And that's unfortunate, right? It would be nice if all the actions were real actions in some sense, and all the sort of subordinate, incidental stuff could happen behind a cloak or a veil, but it doesn't actually work that way. And so we have this system where we use convention to rediscover a time model, or a physics model, even if you want to call it that. And we rediscover it in subsystems or individual objects. And it really doesn't work. And in particular, it doesn't compose. Right? I have an implicit time model and a model for identity around a little thicket of objects over here. And I want to interact with your system. And you have a model over there. But how do we coordinate across each other? Right? I've already got my lock discipline in play. You've already got your lock discipline in play. And we're kind of stuck. And this problem is really a problem of modeling poorly even before you add concurrency and parallelism to the mix. So one of the things that I want you to take away from this talk today is that we don't have a problem with concurrency and parallelism. Right? We have a problem with modeling reality, and concurrency and parallelism suck for us as a warning sign that we're doing it wrong. Right? But it sucked already. And concurrency and parallelism are just making that more obvious. What's the difference between concurrency and parallelism? There's a great blog post linked in the slides, and it's great not only because the original blog post, but there's a long comment thread with people arguing back and forth about what concurrency and parallelism mean. Since I'm obligated by the title of this track to relate this talk to concurrency and parallelism eventually, I thought it would be a good idea to define them so that we can kind of agree what we're doing. They're very often used, you use one of these words and then you throw the other one in for emphasis. Right? We got problems. Our system is concurrent and parallel. But these words actually do mean something, right? Parallelism is about making stuff go faster by decomposing a problem, right, into subproblems that can be dealt with. Concurrency is about multiple things happening at once. It's about communication patterns. It's about, and Dale talked about this in his talk, it's about modeling the real world where different things are happening and different things are going on. Right? Concurrency is about modeling that. Why do we conflate these two things? There's a lot of reasons, but one of the most interesting is that parallelism becomes concurrency unless you think functionally. Right? Because if I take a functional program that's composed out of pure functions and I decompose it and run it in parallel, right, I have not introduced any kind of possible alternate orderings to my system. Right? I know what kind of result I'm going to get because all the sub-pieces are pure functions. If I'm not building with pure functions, then parallelism immediately becomes concurrency as well, whether you like it or not. So there is definitely a lot of overlap between these things. We need to switch models. There are a lot of different models that we could switch to. You've heard about the actor model already today. That is one possibility, useful. We're going to talk about another one, which is Clojure's approach. And before we do this, we're going to talk about Clojure syntax. So people who haven't seen Clojure before will be able to read code examples. How many people have not seen Clojure syntax before? So about 50% of the room. We're going to go through this very quickly. Clojure is a language that runs on the JVM, and it aspires to deliver JVM features directly, which means that we don't make new things or wrappers for things. And so if you know the data types that are available in the JVM, you already know a lot of the data types that are available in Clojure. Strings are strings. Characters are characters. Integer types are longs. Arbitrary precision integers are big integers. Doubles are doubles. Booleans are booleans. Nil is null. Yada, 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 et cetera, et cetera. Right? So these things map directly to things that already happen on the JVM. On top of that, we have 4 data literals. A list is a singly linked list, and you can tell that with parentheses. Right? That's the literal. Vectors are an index collection, so something that supports fast random access. And so vectors syntactically are in square brackets. A map represents a map from key to value, and the colons there are keywords. That is a type that is well suited to be used as keys. It's not the only thing you would use as keys, but it's a type well suited for it. And then a set literal is also in the curlies, as are maps, but has the pound prefix. So we have 4 data literals. And I will just also say here that everything nests. Right? Anything could be put inside anything else. So I happen to have used keywords as keys in maps, but you could have made a set of maps of vectors of lists a key in some other map. Right? Everything nests arbitrarily, and that all works because all these collections, partially because all these collections are immutable. Right? None of these things, none of these collections ever change. So you instantiate one, and then if you want a collection that's a whole lot like that collection but a tiny bit different, then you instantiate another collection that is a whole lot like that collection but a tiny bit different. Here's a function call in Clojure. So this is one possible hello world program, println hello world. The semantics are the first thing after an open parenthesis is the verb, the function call conceptually, and then 0 or more arguments. Here we have 1 argument, which is the string hello world. Notice that Clojure's function call doesn't introduce any syntax beyond the data structures. Right? So you already saw list, vector, map, and set. You're not going to see any more syntax. That's it. Right? Game over. If we want to define functions, Defin defines a named function. The first argument to defin is a symbol, the name of the function. Second argument is a documentation string, optional. Third argument is the argument list, which is a vector of names that will be bound to the arguments. And then the body of the function is calls to other functions. In this case, calling the stir function to concatenate its arguments together. And again, that's the interpretation, but all the pieces are just data. The last little bit of syntax that I will show you is that Clojure has metadata. And so when you see the caret in front of something, that thing is metadata on the next form. So this is adding the metadata string to the symbol greet. And that's telling the compiler that this function, greet, returns something that's of type java.lang.string. And there's a little bit of syntactic sugar going on here. Metadata is always a map. So it's always a collection of key-value pairs. But the use of metadata in programs to identify types is so common that if you say caret string, it expands to caret tag string, which is a map saying the tag of this thing is string. So that you could write it out the long way if you wanted to. I've chosen to write it in short form here. Yes, question?
So you could put this type, you could declare on the arguments as well as on the function itself.
Yes. So the question was, can you declare this type on arguments as well? You can. And this is not what this talk is about, but I'll go ahead and say that when you put type hints like this on, then type hints flow with inference, and you get performance equivalent to what you'd get on Java itself. And so you can take a Clojure program and get it to where you want it, and then find your inner loop and go make it crazy fast by adding type hints if your performance issue is driven by type reflection. So that's Clojure. Now we're going to talk about the pieces. So we're going to go back and revisit time, identity, values, perception, and action, and look at how Clojure implements each of those. Clojure is built on values, and Clojure's values are what are called persistent data structures. And the important thing to think about with values is that if I have a vector with 1,000 things in it, and I'd like to have a vector that's a lot like that vector but a little different, so a vector with 1,001 things in it, how do I get there? The first vector is immutable. I'm not allowed to change it, so what do? I copy it. Right? How is the performance of that? It sucks. Right? Because we go to O of n and worse for all kinds of operations that should be order of constant time or order of log of something. And the trick is that for every kind of data structure you want to use in everyday programming, there are data structures that are called persistent data structures that allow copying while preserving the big O of time and space that you would expect from your collection class. Right? So Clojure's vector delivers, I want to copy this vector and give you a new one with only constant space addition. Right? So I don't actually get 1,000 more things when I copy that vector. And these data structures are awesome, and they're already being introduced in other JVM languages as well. And if you haven't seen these before, it would be really good to learn them because everyone will be doing this in a few years. This is absolutely the right way to go. It's the right default. Immutable data structures are not the right default. They are useful in some cases, but they're certainly not the right default for programs. The easiest way to understand a persistent data structure is to think about the example that anybody could implement in their sleep, which is the linked list. Right? This is easy. My favorite animals are tern, rabbit, and tiger. Martin's favorite animals also include the newt. Right? But notice that we didn't have to copy all the other things, right? He just happens to point into the list. And Dale made this exact same point this morning when he was showing the stack, right? Showing that the stack could pick up new stacks that represented somebody else's interest in the stack, what they had pushed or popped in the implementation, and you get the same idea there. Well, that's great for lists, but what do we really want? We want vectors and maps and sets. And in Clojure, those are implemented as bit-partitioned trees. So think of a tree as a slight generalization of a list, and then what you end up with is, over on the left, I have a tree that has 4 items in it, and now I get a tree that uses all those bits and adds a couple of additional items. And how much work do I actually have to do to copy that? What's it driven by? I don't have to copy all the old items because my new tree is going to point back into the old structure. Which, by the way, is safe. Why? It's immutable. Right? This wouldn't work with mutable data structures, but it's perfectly okay for me to do what's called structural sharing here. So what's the big O of this going to be? What's it going to be driven by? It's going to be driven by the elements that actually change. We can't avoid that. But it also has this other piece, which is how deep the tree is. Right? How deep the tree is going to determine how many pointers in the tree that we have to update. And so we want to make the trees branch out really quickly. And so Clojure's data structures are built on trees, or tries, depending on how you want to pronounce it. Both are acceptable. That have a 32-way branch factor. Now, this means that Clojure's data structures do not give the exact same performance guarantee that Java's do. They give something that's slightly worse in an academic computer science sense, right, which is log base 32 of n. But how quickly does that actually grow? It's slow enough, right? Because what you could do, you could actually say Clojure's collections only support billions of things, and they work in constant time, and the constant is 6. Right? Right? So you could argue that in fact that it's a constant factor. It is log 32, but it doesn't matter. Right? And so this is how we get these structures that have these characteristics, and we get to use them for all of our different collection types. So that's the value part of the story. The second thing that we want is some way to deal with identities. Some way to say, here's something that currently has this value, and at some point in the future can have a different value. And in Clojure, these are represented by references, or refs. So a ref points to a value, and then Clojure provides an explicit semantic, and there's more than one choice here, for saying this ref, Stu's bank account used to be 100, and now we add 10 to it. It's now 110. There are multiple different semantics for doing that update. They're all atomic. They're all thread safe. And what happens to this old value after the update? It depends, right? What happens if one of you is passionately contemplating that old value? Knock yourself out, right? This is what garbage collection is for, right? When you stop passionately contemplating the old value, it'll go away with garbage collection. And if you want to contemplate it for years, then that's perfectly fine as well. Contrast this with mutable state and locks. So in traditional Java programs, you'd have a variable, and it would point to something, but the thing that a variable points to isn't a value, except occasionally by accident. Right? When does a Java variable actually point to a value? When it happens to be public, final, blah, blah, blah. So by convention, you could have things be values, but they're not going to automatically be values. And what is the automatic strategy for protecting this thing from concurrent access? Well, there's not one. Right? I don't have an explicit semantic. And what happens in a Java program if you forget to lock the thing? Behaviors it's indeterminate, right? But it's not good. It's indeterminate bad. Many years ago, I did the JDC Tech Tips. I don't know if people ever read the Java Developer Connection Tech Tips. And I did this tech tip on concurrency problems. And I wrote this thing that showed, here's some unthread safe code and how it could blow up. And the editor for the tech tips couldn't get it to fail. Right? So he kept running it on his machine, and it wouldn't fail, and it wouldn't fail, and it wouldn't fail. And he finally said, this problem sounds like it happens so infrequently that maybe it's not a problem that would be of interest to our readers. Now, we know the opposite is true, right? The problem that is there but is incredibly hard to reproduce is the worst kind. There is no single strategy that you can put in play, and there is no way to communicate to consumers of your code how they're supposed to apply locks to try to bandage the situation we're in here. I mean, what would you do? I mean, what is the way in Java, and correctly so, that we communicate abstractions to other people? What is the mechanism for abstraction? There's one good one and several bad ones. Interfaces, and then classes that implement those interfaces, right? Interfaces are our mechanism for abstraction. What about an interface tells you which things are identities and which things are components of identities and which things are values? Nothing. Right? Nothing in the way we model stuff allows you to make these distinctions. Right? What in an interface tells the consumer which things they have to lock when in order to make the program work? Nothing. Yeah, a comment. If you're lucky. The next thing that we want to have is perception. And the way that perception works in Clojure is that we already have this notion of identities. And so the dotted box here is an identity, and time is actually flowing to the right. So there's a point in time v1, there's a point in time v2, there's a point in time v3, and a point in time v4. And all of those points are values. And the f's are pure functions that take one value and return the next value. So instead of doing a bang away mutate in place, we say take my address book and associate in a new key for some friend I just met at the conference this week, right? And then we add that thing to the collection. And then perceivers get to hang out down here and look at values. In this model, does reality slow down as the number of perceivers increases? No. Right? This is really important. Now, if you're programming with locks, does reality slow down as the number of perceivers increases? Yes. In reality, does reality slow down as the number of perceivers increases? No. Right? The locking model is abhorrent to reality. And it's really bad because it basically says that perception and change really go through the same pipeline, and they impede each other. And that's not how the world works. Right? We can look at each other all we want to, and that does not impede change in the world. Finally, we have actions. And actions are built around a set of function calls that are called the unified update model. And you'll see why unified in a moment. So if you want to change something in Clojure, you call some function that does a change of state. And there are multiple named functions that are going to be plugged in under change state there. And it takes a reference, which is an identity, so the current value of Stu's bank account, a function, which is going to change the value of Stu's bank account, and then some number of arguments if the function needs arguments. Right? So usually when we're modifying my bank account, I want that function to be plus, or even better, times. Right? And I want the arguments to be large positive numbers. And the function gets the current state of the reference. It becomes, function return becomes the next state of the reference. And if anybody wants to be looking at the old version, they are perfectly welcome to do so. And there is no locking, and deadlocks are impossible. And readers are never impeded by writers. Right? Action and perception do not flow through the same pipe in Clojure. Okay? That's really wrong. Right? Perception is cheap and free in reality. It is cheap and free in Clojure. And the reason this is called the unified update model is that you can choose update semantics. And the choice of function here determines what update semantic you want. Actually, you have a combination of the function and the type of the reference. And those update semantics are guaranteed by Clojure. Right? They're not going to be broken. If you misuse them, it's going to throw an exception. Right? It's not going to be, oops, you forgot to lock, and now your data silently gets corrupted. Refs, I'm sorry that this word gets double purpose. This is kind of the aggregate name for things, but it's also the name for the most famous of the reference types. Do updates via software transactional memory. Agents do asynchronous uncoordinated update. And atoms do synchronous uncoordinated update. These are not all the possible strategies that fit in this model. In fact, if some of you have watched Rich Hickey's recent talks about pods, there is actually a strategy here that's built around locking as well. So you could actually have locking be buried down in a strategy, and that probably will be released in a future version of Clojure. It's not the most common one you'd want, which is why it's not there now, but if you wanted it, and that locking would not have any of the liabilities of the locking we do today, because all the lock order would be managed inside the construct in such a way that you got deterministic results and no possibility of deadlock. So we'll start by looking at atoms. They're the simplest form of identity. And atoms are really just a model on top of compare and swap. And so the idea here is that we're looking at values, we the perceivers. Somebody does a swap, so swap bang. They apply some function to that piece of state. And under the covers, you get a spin, compare and swap. And if you try to make an update and you couldn't, then you get bounced out. And actually you get automatically retried. And your call to swap is going to return the value that you got back when you were done. And I wrote a simple example to show this. The blog link is there. Actually, this was started by Lau Jensen. Wrote the original blog post, and then I've done some modifications to it. But what this is a game of life-like simulation. This one is Brian's functional brain, but same idea. And so you have rules about life. Right? You know, if I have the right number of dots next to me, I'm going to snuggle up and reproduce, and there will be more dots. And if I have the wrong number of dots next to me, I'm going to be lonely and sad and die. And then you set this thing loose. How many identities are there in this system? How much mutable state is there in this system? There's more than one choice of how you model it, right? You could choose to model it more than one way. The way that Lau modeled it, and I followed this, is that there's actually one piece of state in the entire system, the board. Right? So the board has a value for every spot, what its state is. And so there's a pure function that will manufacture a board in an initial state, and it's represented by the keywords on and the keywords off in a bunch of different spots. And then there's a pure function step that, given a board, returns what? The next step of the board. And how much does that cost? Not much. And then the entire mutable state of the program is this one line. Swap stage step. Swap, take the state of the stage that it was currently at, apply the step function to it, and now it's at its new state. And then we've got swing and JavaGook running in the background and drawing that state every time it changes. What does this imply for testability of programs? It's pretty sweet, right? Because where did all the interesting stuff happen? The interesting stuff is cleanly separated from the mutating stuff, right? Which means that you write a unit test that actually tests this function, right? This is where the nastiness happens. And actually the cool functional nastiness, if you want to go look at this, happens in this function called torus window, which lazily creates a cursor that's in 2 dimensions that slides over the thing and figures out how much state you need to know to determine the next state. And it turns out that the way these tests are written, they're actually visual, right? I wrote a little program that took little pictures and said, here's this input picture should result in this output, and with ASCII art, right? And I made a macro that compiled the ASCII art into the test. And so that's the entire test suite, is pictures that show what the state. This is beautiful, right? And you don't have to worry about mutable state at all, and all that work happens just in that one spot. A second choice is to use software transactional memory. And the important thing about software transactional memory is, unlike atoms, it allows coordination. So a lot of times in systems you want to, this is where locking gets hard, right? I need to lock 2 different things. I need to have a lock that somehow aggregates together multiple things. The difference is with transactions that any item that joins a transaction automatically gets grouped together. So here we have the world timeline, and at some point in the world timeline, the first 2 rows both participate in a transaction and get updated. And then the second, third, and fourth rows participate in a transaction and get updated. And then the first, third, and fourth participate in a transaction, and then just the second, and blah, blah, blah. And all these updates happen. And from an API example, I'll show it really simple. This is a thread-safe chat application, minus the view part for the web app if you wanted to do it that way. So I'm going to create a top-level thing called messages. It's going to be a reference to all the chat messages in the program. How many chat messages do we have when we boot up? None. We can check that. So anytime, this is perception, by the way. These are the APIs for perception. So I've gone on and on about that. We should actually, there's the syntax, right? You can say deref. That means I want to look at this. How much does the world slow down when I look? None, right? And deref is so important that there's actually syntactic sugar. You can say at messages, right? Give me what's at this address. Then the actual API, instead of being called swap, is alter, but it takes the same kinds of arguments. So we alter, and maybe we pass in some update function and get the args, and then the reference gets swapped atomically to the new value. Here is the thread-safe update. So to add a message to the database, we start a transaction, we call alter messages, conj, short for conjoin. Conj is a beautiful little function. Conj builds collections in the way God wanted them built. And so you can conj onto anything. It's polymorphic pouring something into a collection. Right? So in Clojure, you can conj onto any kind of thing. Right? I can conj onto records, I can conj onto objects, maps, sets, whatever, and it will add things in the way that object knows how to add. So in this case, it's a vector, so it's going to add at the end, because that's the default update in parentheses semantic for that. And so this says, in a transaction, update the messages. Now, in this particular case, I'm not involving a second reference, so you could make a legitimate argument for just using an atom here. But presumably, I'm doing this because somewhere else in my system, I need to look at the state of the chat database and some other thing at the same time. Now, Clojure gets a lot of positive and negative attention because of STM. Right? One of the things that people say is, well, in the JVM world, if you run into problems with concurrency and parallelism, which you remember that means concurrency and some emphasis, right? If you're having those problems, then you have to switch to either Scala because it has actors or Clojure because it has software transactional memory. That does a disservice to every noun in the sentence, pretty much. right? Because Scala has libraries to support other models than that. Clojure has libraries that support other models than that. And so I want you to go away today knowing that Clojure has a model for perception and a unified update model for action. Right? Software transactional memory is one instantiation of it. The other thing that's important to know about STMs is that they're not all created equal. Some of you may have seen that Microsoft abandoned a software transactional memory project a while back that led to a conversation on the Clojure mailing list of, Microsoft thinks it's a bad idea, so it must be wrong kind of conversation. And the difference was that a lot of people that are trying to do software transactional memory are trying to make it work as magic fairy dust on top of existing mutable applications. Right? And magic fairy dust software transactional memory isn't a good idea. Microsoft was right to abandon it. Clojure's doesn't work that way. Right? It does not behave in that way. And so there's a ton of work that's gone into Clojure's STM. If you go and do a literature search on STM, you're going to find a lot of bitching and moaning about STM problems. And those are primarily problems of specific implementations. And the biggest of which is specific implementations that try to be magic fairy dust on top of mutable data, right? Which Clojure is not trying to do. So if you want to critique Clojure's STM, make sure you actually critique Clojure's STM and look at the actual properties that it has. So agents are a third form of identity, and agents represent asynchronous. Right? I want this to happen, but it doesn't have to happen right now. And so I send a function, and the function gets lined up in a queue, and then it gets popped off the queue, applied to the object, and off we go. What does this sound like? It has the word asynchronous in it, so what do people immediately go to? Actors. Agents are actors, actors are agents, I get it. No. Agents are not actors. Right? There are two extremely important differences. One thing that agents can do that actors can't, and one thing that actors can do that agents can't. Actors distribute this queue if they want to. Right? Actors let you do things across processes and across networks, and that's really good, because most of us build systems that work that way. But agents are part of Clojure's perception model, right? So they can be observed. What's the model for observing an actor? Send it a message, which is what? That's coordination, right? I want to coordinate with this thing, right? And that means that the actor might have to slow down, right? If a lot of people want to observe it, what happens? Reality slows down. Both of these models are valuable. They're valuable in different places. Okay? I would argue that agents are valuable. Agents are probably actually less valuable overall, but they're valuable at more granular places in process. And actors are valuable in a broader context. The description for this track included 3 different approaches to concurrency. This is just grabbing nouns out of the track description. Locks, STM, actors. Those things are interesting, and it's important to understand them all. It's not a useful way to partition the world, especially when people partition it by saying that language X specializes in this one and language Y specializes in that one. The people who care about this stuff are trying all of these things in a bunch of different languages. And so all 3 of these things are available in Scala. All 3 of these things are available in Clojure. There are differences in how they're presented, but all these models are around. And I'm really not happy with this taxonomy slide, but I'll throw it up anyway. I think this is the problem with these taxonomy slides is that they imply more categorization than I really want to, and I think we're still learning this stuff. And in particular, I want this taxonomy to be 4-dimensional or 5-dimensional. You can already see that I'm struggling with the 3rd dimension because I've had to layer in a 3rd dimension by having 2 different names, right? Uncoordinated synchronous, coordinated synchronous, whatever. But this will help you come back and look and say, okay, uncoordinated synchronous, atoms. Coordinated synchronous is the STM and later pods with locks. Uncoordinated asynchronous is agents. And then, if you don't want to leverage locality and perception, if you're able to presume distance or you want to take advantage of distance, then you can use something like the actor model. I have a slew of slides about refinements and additions and details on top of the basic model that I've laid out. But I've laid out the basic model at this point. I'm done in a certain sense, right? What Clojure wants to give you is perception unencumbered by action. And it's amazing how systematically across the industry we don't do this well, right? All kinds of things, and not just programming languages. Route perception and action through the same pipe. Reality doesn't do that, right? When I look at Martin, I am not sending him a message with my eyes and getting a message back, right? It's ambient. I'm just perceiving him, right? Light is bouncing off of Martin, coming from whatever galaxy it came from, and I'm seeing him. So, before I start talking about details, any questions? Yes?
Do you have any mechanism for enforcing a non-side effecting function going into one of these?
A good question. Is there a mechanism for enforcing the functions? No, this is not Haskell. This is consenting adult dynamic language land, right? This is also run on the JVM land. So to do that, we would have to make ourselves more distant from the JVM than we want to be. And I said that I gave a talk about simplicity in Clojure yesterday, and the place where Clojure compromises with simplicity is in reaching the JVM, right? And if you wanted to build enough of a layer to have that, you'd have to wall off the whole JVM, and we don't want to do that, right? We want to have access to that stuff. So that's a straight up engineering trade-off.
But within the language, there's some guarantees for that, like messages are not being sent. Sends don't happen until a transaction completes and that kind of stuff.
Yeah, there are a lot of nice things that are guaranteed where it's possible to do so, but what's not possible to guarantee is a blanket compiler enforced. I know these things don't mutate and these things do, right? We're not about that in Clojure. I mean, it would be nice, but you would trade off a lot of other things to get it. So, the devil is in the details. Everything I just said is a really nice model, but it takes a lot of work and sweating particular things and thinking about how to make the pieces fit together to actually make it pleasant to use. So the next several slides are going to talk about things that do not do anything but add important details on top of the main story. Right? This is all just additional stuff you might find useful. The first thing is that Clojure is thread ready. Right? It's thread ready in that everything in Clojure is thread safe. Right? Things are either values, which means you can look at them, or references, which you can look at them. Right? That's it. There's nothing else. Again, caveating out, Java interop. Right? If you bring in something via Java interop, you get what you asked for. All Clojure functions are callable and runnable. So if you wanted to integrate Clojure into another JVM language in some way, you would have an easy way to grab things and call them. And Clojure has a simple way to throw work onto a thread pool with future. So you could just say, this particular example is a Google fight. So behind the scenes here, estimated hits for goes out to Google and does a search for term 1, does a search for term 2, and then eventually returns a map with the third future that waits for the two things to be ready that has what are the values of this. Right? So you can say, so this is a really easy way to say, I just want to have concurrency by ways of saying I want to launch a bunch of things and then I want to wait for all the results to be there. There are other ways you could do this as well. Now, a second interesting detail is transients. So Clojure does not have purely functional data structures in the sense that inside the data structure, mutation happens. You're guaranteed not to ever see that mutation. Right? And of course, you already have these kinds of guarantees in the Java world. Right? There are certain things that there are certain visibility guarantees in the Java world. So you cannot make this perform well. You cannot make the things that we've talked about here perform well unless you're willing to allow super secret mutation inside of objects and have walls that prevent that from becoming visible. In particular, Clojure has a feature called transients that says if I am building a collection, right? So if right now I have one object in my collection, I'm going to go do stuff that puts 1 million objects in this collection, right? By default, every one of those intermediate steps would be a value that could be perceived by the outside world. But maybe you don't want anybody to perceive it yet. So you don't want to pay the overhead of having that be possible. Transients allow you to turn that off. They allow you to say, you know what? I'm busy building this object. I'm birthing a new object. I don't want to do all the work to make each intermediate step visible to the outside world because I don't plan to hand it out to the outside world. Now, what happens if as a programmer you start using transients and then turn around and hand something out to the outside world? It throws an exception the minute you try to do anything with it, right? So this is, again, it has to be safe to be useful. And so this is an example of a kind of guarantee that can be made. Another thing that's really important is thinking carefully about your updates. Right? The future, if we're going to worry about living in a multi-core world, and we are, the future is all about trying to find the minimum thing you can say about the update. Right? One thing you don't want to say is read, ponder, write. Right? That sucks. We all know that sucks, right? Because what does that do if other people actually also want to be interacting with the system? Right? When I come back from pondering, maybe things have already changed. So what we want to do is send the function to the data. And notice that the API in Clojure does that, right? When you're updating an identity, you're actually sending to the identity a function and some args. You go do it, and then you can implement the concurrency strategy inside the reference type, and then give me the result. But there are more things there than that. In particular, you want to be able to say a particular update is commutative, right? Which is to say, I don't care what order it happens in. And just for getting through it quickly, I'll just show an example. Here's an example of something that is not safe for commute, right? Getting the next ID. If I were using transactions to make an ID delivery system, so I'll give you ID number 1 and you ID number 2 and you ID number 3, then we do care about order because the return value matters. You're going to consume the return value. So this thing has to be done with the regular alter, which is how you update things in a transaction. But what if I'm not handing out IDs, I'm just incrementing a counter? So I want to know what the total number of people who used this thing today was, or the total number of aliens that are on the screen or whatever. I'm just keeping count of something. And I don't care which one got there first, and I'm not assigning. There's 50 aliens on the screen, but I don't want to assign each one a unique number. I just want to know that there are 50 aliens on the screen. Then I don't actually have to say alter here. I can say commute. And internally, that allows Clojure to make a variety of performance optimizations inside the STM to say, you know what? The value I give you back may not be the real value you get updated to because you told me you didn't care. Right? You told me you want to make this update happen. You want it to be coordinated with other things, but you don't want it to cause transactions to fail. And the place where this is really awesome is where you have a transaction that touches an expensive resource and a contested resource. Right? And the contested resource is commutative. Right? So then you do a bunch of work on the expensive resource, and then you want to update the contested resource that a lot of other people also updated, and you're like, oh shit, I missed. Somebody else got in and did it, and the transaction restarts, and then you go do all the heavy work again. If you can identify that contested resource as commutative, you can fly, right? Because now you don't have to wait for other transactions to get out of your way. The agent thread pool in Clojure has 2 different varieties, send and send off, and these are for things that are compute intensive versus things that are I/O potentially intensive. So send says make this agent do some work on a fixed thread pool. And a fixed thread pool is what you want for something that's compute intensive. Why? So you can tune it to your number of processors. And everybody knows, we should track down the origin of this, but everybody knows that if you have n processors, how many threads do you want in this pool? N plus 2. I mean, everyone who does this does n plus 2. I don't know why, but it is not like 100n or n squared or something like that, right? Some function of that. So you have a fixed thread pool. But if you're doing something that's I/O intensive, blocking I/O, right, you don't want to be stuck on a fixed thread pool because you're not actually using, right, you're not using the thread pool to act as a meter for how many processors you have. And so there's a separate API. There are also APIs that don't conform to the unified update model that are used for a hard set. So instead of sending a function to a reference, you can just say, boom, make this thing's value be that. You don't use that very often, but it's nice for putting things into initial states. So normally you're going to do alter, swap, and send. But every once in a while, you need to say ref set or reset to say, let me put this thing back into a clean, good state. We also have validation on references. And this is very interesting when you compare to the OO approach, because these validations are validations on the updates, not on the things. Right? Validate the verbs, not the nouns, if you will. And so you can do something like validate message list is a function that verifies that everything in our chat has a sender and a text. And then you can say when I create, this is my little thread-safe chat program again, this time when I create it, instead of being a ref to just an empty list, it's a ref to the empty list with a validator that says all updates to this thing must follow this rule. And now we are doing the validation not in the noun, right? Not down inside of an object where it's like you do something to me and I ask if it's okay. We're doing it in the verb. Now, nothing makes me do it in the verb in Clojure. Obviously, I could still validate nouns, right? I could still make functions that manufacture data structures and have them validate constraints. But if you want to, you can do the validation in the verb. The thing this is most analogous to is database constraints. Right? Database constraints say, I know that you're happy with the update you just did, but we have a rule about the whole table that says, you're not allowed to do that. So this is kind of analogous to that. You can also, and Creston was mentioning this before, you can send to an agent from within a transaction. Well, transactions get retried, right? So the STM will retry things. So what would you want from an agent send inside a transaction? You don't want the send to just go to the agent every time the transaction gets retried. You want it to be held up and sent off later. And so you end up with, this is a really trivial example, but this program actually makes my thread-safe chat database persistent. So what I do is I say, inside of a transaction, I grab the current value, I update and grab the current value in snapshot. So I alter my messages to add the new message, and then I send off to the backup agent a function which spits something to a file. Right? So I spit to a file the current snapshot. So now, every time a transaction completes adding a message to my little online chat, it also kicks off a background thing that saves the entire state. Now, this is not a replacement for the ACID properties in a database. Right? This does not deliver ACID Y. What happens if we flip the power switch off after the in-memory transaction but before the write? Right? It's not durable. Right? So if you need to have the ACID properties, you should use something that has the ACID properties. This is why we run on the JVM. I hear a rumor that there are a few APIs that you can call from Java that let you get to that stuff. Right? So there's no aspiration to durability here. So where are we? The time model beats the pants off the total control model. Nobody disagrees at this point that the total control model is a bad way to model a world where you have multiple things happening, where you have concurrency. But the time model is not necessarily the only way to do it, but I think it's a very good way. And the reason that the time model is so terrific, first off, it pushes us in all the right directions that all the different programming actors also push us in this direction. Right? It pushes us towards doing a lot of things with functions and immutable values, and that's great. But the thing that the time model delivers that's unique is perception being free. Right? Perception working the way I think it works in the world. And now is really a good time to be switching, right? Because concurrency and parallelism are going to make these things a bigger problem for you, right? The model was already poor, but now we have like a proximal pain point that we can say, oh, manager, we have to do this now, right? We can't take advantage of multiple cores until we start coding in this way. And Clojure's approach to this is unified, right? So everything has this perception model, but it's also multifaceted, right? It's not a one-size-fits-all, you must do it this way. Some things fit software transactional memory, some things fit locking, some things fit agents. You can use the thing that you need for your particular problem. And with that, I want to say thanks very much. It's been a great pleasure. This is my last talk here this year, so I'm finishing up, and I think we have 3 minutes for questions. Yes?
Is there any apps built using some of these concepts? Do you have any sort of real-world sort of use cases?
So at my day job at Relevance, we are doing probably about 30% of our code across a 25-person team in Clojure. And the important thing that I would say to you, and I think this is true for this model, it's also true for actor model systems and other things that people are doing, is that it's astonishing how little identity you need in most programs. Right? So yes, we have a lot of code in production that uses this stuff, but by uses this stuff, I mean, here's 4,000 lines of Clojure code with one identity in it. Right? So for example, the Clojure web framework Composure has one identity in it. And so the stuff that I showed today is really important when you need it, but step one, if you're trying to get righteous Clojure style, step one is definitely start trying to write everything with pure functions. Right? Pretend like you're constrained to pure FP, and then whenever that hurts, you have this. But the FP part is really important too, and most of the industry is not doing that yet. And so yes, there's experience with this, but I would temper that by saying that these constructs in most programs, they represent a tiny fraction of the actual lines of code you write. And most of the code you write is pure data or pure functions. Take one more question, yeah?
That multifaceted stuff always be seen as kind of a negative thing, because it's kind of, you leave it up to the developer to decide what to use, and hey, I like STM, I use STM all the time, but someone has to decide now what's the optimal thing to use for a specific one.
So the question is the multifaceted nature, particularly the multiple different update styles, possibly a negative? I don't think so in this case, but I'll explain my reasoning, and you can decide for yourself. I think that if there's one right choice, and you give a developer multiple choices, you're just making trouble. But if there's a variety of different choices that are useful in different circumstances, and there's no reasonable way for you to automatically detect that and choose for the developer, then you have to give the developer choices. And these are all real choices. They're all real things. And I mean, locking represents in some sense only one choice, and that hasn't helped us very much. So I think in this particular, there are scenarios where that is a trade-off. So there are some projects that I'm working on right now where there are other things where we're giving a developer a choice because we don't know how to decide for them yet. But in this case, I don't think these will ever go away. Right? Knowing that you want something to be synchronous and coordinated versus asynchronous is not something that's going to magically fall out of a language. So in this particular case, I don't think that's a problem. All right. Thanks very much, everyone.